Welcome to Selenetics Vol.3, Part 1, Circling the Square. So far, we've established that the moon is a map of the Earth. All the coastlines match on all the continents. In Africa, the Sahara Desert is a collection of lakes, exactly like its ancient form. Even the coastline of Antarctica under the ice is a perfect match for the master projection in the sky. This episode will cover one method for creating a moon-centric Selenetics coordinate system through a series of transformations of a standard equirectangular cylindrical coordinate system. We'll use EPSG 4326, a 2-to-1 ratio coordinate system where each graticule is a perfect square. As a standard, the left half square is the western hemisphere and the right half square is the eastern hemisphere. We'll mark the center of each hemisphere as pseudopoles, the west pole and the east pole. When using a conic equidistant function to polarize rectangular coordinates, the west and east poles act as anchors or focal points for the polarization. The end result are polar coordinates comprised of curvilinear quadrilaterals called polar rectangles. This is the azimuthal equidistant projection. The three primary axes of rotation in three-dimensional space are roll, pitch, and yaw. Roll is rotation around the front to back axis. Pitch is rotation around the right to left axis. Yaw is rotation around the up to down axis. From the north center polar projection, pitching -90 degrees brings the equator to the central latitude. Note that the equator is not just the central latitude, but also the entire perimeter. Currently, the equator, 0 latitude, is the central latitude. We need 60 south to be the central latitude. This requires latitudinal inflation of all areas south of 60 south by a factor of 3, and latitudinal shrinking of all area north of 60 south to 3/5. The central latitude is now at 60 south. We'll call 60 south the greater equator. The top and bottom halves, the greater north and the greater south. The left and right halves, the greater west and the greater east. The large distortion gap in the graticule is at the anti-meridian. We want that gap at the prime meridian. So we will yaw the entire projection 180 degrees. Next, to match the Selenetic orientation, we have to invert the southern half and rotate the northern half 180 degrees. We'll achieve this by flipping the whole projection horizontally, then flipping the northern half vertically. This gives us the pseudo-selenetic split lobe azimuthal equidistant projection with differential radial scaling and greater southern hemispheric reflection. At this point, all the continents are generally aligned to the Selenetic projection. In order to fit it perfectly, a three-dimensional spiraling S-curve wave function is applied to the coordinates. On the right is a skeleton of the wave function, showing only the prime meridian, anti-meridian, equator, and 75 south. The mathematical details of the wave function are in the advanced lessons. Let's rewind. Reverse wave function. Unflip north vertically. Unflip whole projection horizontally. yaw negative 180 degrees, return equator to central latitude, pitch 90 degrees, depolarize. These steps can be applied in a variety of ways. Let's separate north and south, then expand to the graters. We'll combine the southern flip with the northern 180-degree offset, creating a dual horizontal flip centered on the west and east pseudopoles. Then we'll polarize around the north and south poles. This gives us a dual greater azimuthal equidistant projection, which can easily be expanded to the Selenetics projection by applying the S-curve waveform. We can combine depolarization and the waveform to go straight to the greater equirectangular projection with southern hemispheric reflection. The waveform applied to the cylindrical equirectangular creates the cylindrical Selenetics projection. The S-curve waveform varies across the projection, but in general is directionally aligned to the split lobe azimuthal equidistant projection. In the Celonetics projection, longitude lines can be directed to the west and east pseudopoles to create an uninterrupted path from the north to the south pole. The next part of this volume is the data analysis of the geology and structure of the moon. The crater regions which correspond with water, the maria which correspond with land, the ridge crest, rills, and lineaments which correspond with mountains and volcanic regions, as well as various geologic maps of terrestrial Selonetica.